Welcome to Discovering the Unknown in the LSST era. This session is being chaired by Ashish Mahabal, and Jalonli, and myself. I will go through the slides that by now you've probably seen and memorized about rules of engagement for this meeting. Virtual participants should be muted if they're not speaking. We have Jalong monitoring the Slack and the Zoom chat. And so if you want to speak, if you want to unmute, just post it on Slack and we will give you the microphone and the stage. If you are an in-person participant, wait for the microphone to arrive to you before you start speaking. So raise your hand, we'll bring the microphone. You'll be able to ask a question. If you're sitting on the table, it's even better. You just need to press the button and then your microphone is on and everybody can hear you. People get excited and start speaking before the microphone arrives to them, which means that then I had to like run back and forth in the room, and I've done it for the past session. I don't have many miles left in my legs today, so please wait for me to arrive to you and give you the microphone. We have a Slack space. The Slack, I wanted to replace it with a correct link, but I forgot. The Slack link is going to be day 4, Thursday, slot 4P, Discover Unknowns. And use the Slack for asking questions if you are online rather than the chat in the Zoom, because that way we have a record of questions that have been asked, but raise your hand on Zoom. And very important, oh, I had skipped it somehow. Please remember to be courteous and kind to your fellow PCW participants. Respect their space by looking at the button that they have on their name tag and making contact appropriately. Also, some of us are wearing a social battery slider. Maybe give space to people whose battery is in the red, but also perhaps ask if the battery is in fact in the red, because it tends to slide towards the red incidentally. The full code of conduct is available here at this URL. I trust that by now you have read it. And the shortest possible version that I can give you is be kind and treat each other like you'd like to be treated. If you are unsafe at any point, we have an email. So we have an email, Rubin 2023 helpline at lists.lsst.org. We also have 3 meeting participants that have kindly agreed to put their time and energy into the role of on-spot person. Those are Andy Connolly, John Franklin Crenshaw, and Alicia Sugar. And you can reach them at this email, or you can see them at the meeting, and they can help you if you need help and if you have concerns. I don't see anybody wanting to ask questions, so I'm going to move on. We have a packed agenda, so I'm going to ask right away to all the speakers to please stick to these times. I gave you as lesser or equal then. Please stay within the lesser or equal, ideally on the lesser side. I'm going to be done. In fact, Ashish will talk about the TVS anomaly subgroup, so I'm actually in fact already done. Just briefly, Ashish Mahabal, Jalon Lee, Will Clarkson, Harry Hines, Agnieszka Polo, Konstantin Malanchev, and Alicia Villar will give presentations, few minutes each. And then we'll have one slider or even shorter presentations by Chris Linton, Ashish Mahabal, Avi Saha, Patrick Aleo. And I hope that will still give us some time for discussion. I think given the packed agenda, we'll take one question at the end of each one of the slides. Hopefully we can have more questions later. And with that, Ashish.
Thank you, Fed. So yeah, if you can, or I can do that. If you want to take notes, actually, I don't know. So just advance with this. Okay, great. So the thing that we wanted to announce here is that we are proposing to have a new group on anomaly detection as part of the ISSC. And what will be different with this group, of course, is that because ISSC is not associated with a specific science, they can take all your problems related to anomaly discussion and help you with it. So we'd like you to come to the ISSC group with whatever data sets that you think may have anomalies which you want to get rid of or do more science with in either way. So there are people who have expressed interest already, both from ISSC and TVS. You see a few members here, and the group has not formed yet. It is going to be formed, hopefully, provided people agree. And then there has been some activity that has been going on at a very low level in TVS as well. So some of the people that are mentioned here are involved. But again, these people have very interesting ideas in terms of methodology as well as data sets to use. So that is what we'd like to explore. So form a big kind of map to go with that. So what will be the format of the group that we'll have? So there'll be talks that people have already been working on with different things, some like the ones that you're going to see today. But then there'll be lots and lots of discussions, and the discussions will be centered around what kind of data types we can be using, what kind of data sets that we can be using. And many times in astronomy, for instance, when you think of time series, the time series are very gappy, and the standard time series methodology cannot be used with that. And if we want to look for anomalies within that, what happens? So I'll give you an example in ZTF. In ZTF, we have two classifiers. One is called an orphan transient. There are many, two out of many. One is an orphan classifier, which is seen only once, and one is a variable, which is seen more persistently. Neither of them is associated with a host galaxy. So many times when we discover something as an orphan, as time passes, it becomes a variable because now we have more observations. So that kind of things are going to happen with lots of classifiers and trying to understand what those are. But also, one of the main thing that happens is that even within the types of anomalies, there are many, many things. There are rare events. We want to look for them. So we know only one or two, but we want to find more of those. Then there are in-class outliers, which are extreme cases of the kinds that you already know about. So these are not rare, but you are looking for rare varieties of the in-class ones. And then there are inter-class objects. So you know of two classes and something that sits in between them. So there will be subclasses like Blaschko effect, RR Lyrae, for instance. And then, of course, there'll be new phenomena and classes. So what I firmly believe is that there is no such thing as anomalies. Anomalies are typically like tips of iceberg waiting to reveal entire families and populations. And that's what we should be going after. So long as we understand our biases, so long as we understand our limitations, what we are doing, that's where we can be going. And of course, we are going to find many, many artifacts once we start looking for anomalies. And those artifacts are still a good thing to find because those will tell us where we should be making changes in our pipeline to find them much earlier without having to come to the anomaly group or to the level of finding anomalies. So, and that's going to be an improvement in science in general. And there'll be a lot of cross-fertilization, not just within these different methodologies, but also bringing in data sets from outside and seeing how improved we can make our entire pipelines for the project. And here is just a very incomplete the mind map that we have put together based on what people have already provided. So you can see that time series data is one thing, but that's not the only thing. There'll be many things that you can do within images and by combining those as well. And this is something based on what Eric Feigelson provided, for instance, where you can look at various subclasses there. And he apologized profusely because he has only one Python package and 10 R packages. But yes, there'll be many, many Python packages and other language packages also. So there's huge space there to cover within anomaly detection and what we can be doing. And once the group forms, then ideas and talks and discussions will be welcome. And just today, before this session, I was talking to Alex Mars, who is in a different session right now. And he mentioned this, which could possibly be one of the first projects, for instance, that analyze audio data from stress testing the camera system at SLAC. They're looking at these audios when the filters move, when the camera is pointing in different directions, etc., and whether we see any anomalies at specific locations, specific pointings, etc. And that could be something that we could be doing. And I think that is my last slide. Yeah, so I can stop with that. And I don't know if did you say we have time for a question right now? Okay. Sure. Right.
John Longley from the University of Delaware and the Transient and Variable Star Science Collaboration.
Okay. So the detection of the phenomenon that we never before seeing is one of the most exciting thing that Rubin LSST will have the potential to have. So but how can we make sure that our observing strategy will not prevent us from detecting those all new phenomena? So we prepared 2 articles to address these questions. The first one is um, focus on the phenomena in the time domain, and the second one is to be still in preparations is focused on the anomalies in the proper motions. I will talk about the first part, the time domain novelties, and so the second part I will introduce invited Will Clarkson to tell us about the proper motion part. So this plot um, is the evolution time scales versus the peak magnitude of the astrophysical transients. In here, you can different transient located in the different regions in this plot. So supernova, for example, in the right plot is the light curve supernova last hundreds of days, and a kilonova, Y kilonova lasts only several days. So because of this, the kilonova is not detected until recently. And in this plot, there are also large regions that need to have not explained due to the limitations of the facilities. But Rubin IST can open up those spaces if we have the right observing strategies. So our goal is to optimize the Rubin LSST observing strategies to use a model-free approach because we don't know what the new phenomenon will look like, and we design a model-free algorithms to measure the completeness in the feature space defined by the brightness and brightness change, color and color change, and also consider the volume that is explored by the Rubin LSST. And in the plot, you can see that many simulated observing strategies have some gaps between 2 to 14 hours. For the color and the color changes, we investigating the completeness in the time gaps between different filters within 2 days as a matter of colors, and using a statistical mask the KL divergence to measure the difference between the observing strategies and the ideal uniform distributions. And for the brightness and the change of brightness, we use a similar approach, but consider the time range from up to 10 years. And we also consider volume explored by the Rubin LSST, including the depth, the footprint, and the star density. And we combine all those 5 metrics as a single figure merit for the novelties in the time domains. And this is the radar plot that shows the our metrics for the recent simulations version 2.0, and each corner of the radar plot shows one of the elements of our metrics, and the further out, the better is the metrics. And the top performance optims is the rolling cadence. This is the we will recommend for the novelty. This is the animation of the rolling cadence. And we also run our metrics on the new released version 3 baseline and version 3.2 baseline. The result is kind of interesting. The blue one is the version 2, and orange one is the version 3.0, and the green line is the version 3.2. It's very interesting that version 3.2 is the most balanced simulations. And that's all I have. Next, I want to invite Will Clarkson for the second part. Yes, median. That's a median, yes.
Sorry, I didn't have my microphone on, sorry. I'm asking about why is the depth for version 3.2 a little bit less than version 3.0? And I know that Xiaolong and I were trying to figure out the answer before the meeting and we didn't know. But did you have an idea of why? I think I have one.
I didn't figure out.
I think if you were at the observing strategy session, you have already heard this, but for the version 3.2, we added images that can be a very high air mass for a mini survey for the solar system. So if they're a high air mass, they're going to be shallower, and I think they might shift the median a little bit. So I think that this might not be a problem because it's only about images that essentially have been added to the survey in the least possible useful time, like bright time and early in the night, etc. So I think maybe that's okay if it's a little bit small. I'm making a thread on Slack for each speaker, so if you want to ask questions there, you can ask them in the thread. And I see Tony. And, I want to hear them.
Okay, so I don't know if this is a question or a comment, but I think we've been talking about wide, fast, deep main survey. We're going to learn a lot about the time domain and unexpected things in the deep drilling fields where we go and just pound away with continuous imaging. And one of the options there might be doing it with 15-second exposures continuously as opposed to 30. But I think that that's a really interesting sandbox for finding the unexpected in the time domain. So we may end up debating whether or not we want to do some type of observing that's different in the deep drilling fields as opposed to the main.
Yeah, and to
survey.
connect it again to the observing strategy session yesterday, given that it's very likely that we can move to 1 × 30 seconds as opposed to 2 15-second snaps, the question was asked, can you do something hybrid? And it would be complicated because it would be a change of scope and an additional work on the data management side. So I encourage you to submit this as a science motivated justification for doing that. Let's thank Xiaolong.
Thank you. So I will present quite quickly some progress and outlook for the proper motion aspect of this project that Xiaolong has introduced. This is really presenting on behalf of Fabio Ragosta, the person doing the actual work here, but this should give you an idea of what to watch out for. So the idea is to bring in the proper motion aspect of this, as Xiaolong indicated, and I think most people probably already know, but it's worth stating again. LSST will produce scientifically interesting proper motions down to quite good depth. There's this nice quote from an early paper by Jelko and Dave Monet et al. That LSST will smoothly extend Gaia's error versus magnitude curve to about a 4 magnitude fainter level. So there you can think of many science cases in which the attaching a proper motion to objects would also be useful for unknown objects. You find something interesting, one question might be, to what population does that belong? And LSST should be capable of, in many cases, of helping us answer that question. So for example, if your object is too faint for Gaia, or is in a heavily extincted region for Gaia, making it too faint, or it might be transient, it might be only bright enough for a short amount of time to be bright enough for LSST to add proper motion measurements. And so we set out to try and ask the question, how well can we do proper motions on unknown unknowns? And this is where we are. So thanks to the Rubin Sim team, evaluating the predicted proper motion uncertainty for observations from Rubin is straightforward in practice. You can get the straight line gradient uncertainty incorporating measurement by measurement uncertainty, and that can be assessed as a function of predicted strategy because we get the metadata from the strategies, and in a similar way to what Jalong just showed you, we can also assess the proper motion uncertainty. So Fabio Ragosta, you see pictured here, has been developing some metrics to ask these questions. How well can we attach proper motion to unknown unknowns? And I'll give an indication of what these are and what to expect, what to watch out for. So the three figures of merit I'll talk about, this confusion index, this likelihood score, and this transient proper motion metric, all boil down one way or another to simulating a set of populations in position velocity space, doing that for the quote known galactic components, then assessing how well you can measure proper motions of your unknown objects against that background. So I'll go through these three techniques, and at that point we'll sort of reach, I think, where we are for the techniques. So the confusion index I'll talk about first. We're trying to do this in as population agnostic a way as we can, to not have to put in assumptions about what the unknown proper motions actually are. And so one approach to do this is to ask questions like, what is our ability to separate out objects of interest against against background objects? And so imagining a scenario in which an investigator uses reduced proper motion versus color to, let's say, pick out a previously undiscovered dwarf galaxy against the background. What the confusion index does is it parameterizes sort of what fraction of objects would be confused with the background in the reduced proper motion diagram. So as a function of signal to noise and location, you can ask questions like, how well can we do this? I've put the formulas up just for the uncertainty and the reduced proper motion to give you something to read while I'm talking. But the point is that we take account of the fact that in the reduced proper motion color diagram, the uncertainty that does not align with the axes. There are correlations there. And so what Fabio then does is to take the uncertainties in the reduced proper motion diagram there and ask how well can we detect injected dwarf galaxies over the background, and that produces figures looking a bit like this. This is fairly complex. I don't expect you to understand the entire figure just from looking at it, but the idea is you inject Sagittarius dwarf-like objects at the distance of the Sagittarius dwarf, or further away from the Sagittarius dwarf, or fainter intrinsically, and then evaluate sort of what fraction of the objects in that population are confused with something else. So how many other objects are there in the reduced proper motion diagram? And that gives us a tool to ask questions like, for a given observing strategy, how well can these be distinguished? And so that's been pretty much developed, and it now needs to be run on the latest set of simulations to know what the true power of LSST for dwarf galaxies might be. The second metric is this likelihood score, which parameterizes LSST's ability in the vector point diagram to separate out an unusual object from the background. And the idea is basically simulate the galactic population that produces our sort of known objects, and then against that population of known objects, you can ask the question, what fraction of my injected sources do we actually recover? And so Fabio has simulated galactic and unknown populations and then produced a metric that actually parameterizes, to some sense, how well you can find those unknown objects. And that produces diagrams looking like this one, which is from a trial run fairly recently. Don't worry about the details. This is just saying that in some areas you can do this well, in others you can't. And the way that varies is also a function of observing strategy. So that's the likelihood score. The idea is that you imagine a population of unusual objects and then ask what fraction of those can you recover. And then the third is this transient proper motion metric. That's still under refinement. It's been under development for a while. But the big idea is basically, if you imagine an object of interest that of a class you might not have expected to see, or a new object not previously seen, if it's a transient, then it might spend only a limited amount of time at a bright enough level that you can measure proper motions with any particular accuracy. So the question then becomes, for an example set of transient types, as a function of observing strategy, how well could LSST attach kinematic information to this through proper motions? If it spends a long time above the threshold, it may be easier. You could do it for further away objects. If it's a very rapid transient, you have less time to do it, your proper motion will be worse, and therefore your ability to kinematically separate or identify your object with foreground disk or bulge, for example, will be different. This is how it's done. The idea is that the population is simulated. The transient metrics that Xiaolong just mentioned are set to determine, do you find it's a transient in the first place? And then for those, the proper motion uncertainty can be assessed using those observation times following the metadata, as you've heard from Xiaolong before. And the idea is to find for particular classes of objects, of transient objects, what fraction might LSST detect the motion at 5 sigma, let's say. So how well can we actually recover these families of transients and attach proper motion information to them? So those are the methods. Where we are right now, Fabio has finished the implementation of the first two, the confusion index and the likelihood score. The transient proper motion is a bit more involved, and that's actually still under some fine tuning. But the next step, sort of what to watch out for this, is to actually run this on the latest family of OpSims, of simulated strategies, to determine which candidate strategies are least bad for anomaly detection under these different methods. So we welcome input on all aspects of this. So if anything I've said sounds crazy, please let me know. If you have opinions on how we might improve this, please let us know. And to watch out for, there will be, once this is all done, a volume in the special issue FAP.js on observing strategy by Ragosta et al. I'll stop there, and like I say, our group welcomes input, so any comments or questions are welcome. Thanks very much.
Thank you. And thank you to the 4 speakers for sticking to their time. Really appreciate it. Questions for Will? And also suggestions. I think we were very much looking forward to hear suggestions, whether the way in which you think we are doing this is sensible.
Yeah, we can't be the only ones thinking about this. So.
All right. If there are no questions, Ari? So Ari hands, we're going to move to solar system anomalies. We're trying to tap a little bit on all the possible spaces of discoveries of Rubin. So we're going to talk about solar system anomalies now. We're going to talk about galaxies, anomalies in galaxy space, and afterwards, and then we're going to go back to time domain.
It should be around slide 50. 50. I just checked, it was about 50. Yeah. All right, thank you. So I'm talking about finding the unexpected in the solar system, which is an interesting, it's interesting to talk about what unexpected things we expect to find. And at some level, perhaps the most exciting thing will be something I didn't know to put on the list, something that we didn't know enough to expect at all. I tried to think as broadly as possible in terms of unexpected solar system discoveries that might occur. So we could imagine new types of objects, meaning new physical constitutions of objects that we haven't seen before, new types of orbits, new types of behavior, or maybe objects that we already know about and orbits that we already know about, but associated with one another in new ways. And then, of course, interstellar objects, which I won't say much about because they've been very well covered elsewhere, I believe. So in the category of new types of objects, I don't expect that we'll see anything like this. We have a pretty good idea of what the universe can make in terms of what kind of physical constitution of solar system objects is possible in the universe. I don't think we'll find any new ones. One category where we might find something unusual, something we haven't seen before in terms of physical composition, is we might find a fragment of a differentiated body of a type that we haven't seen before. So it's been theorized that Oumuamua was a nitrogen iceberg knocked off an extrasolar Triton analog. I don't think this is likely, but we might see something like that in our solar system. We might see a piece of ice of a different kind of composition that's not an ordinary comet, was knocked off an icy body in the outer solar system. New types of orbits. These are JPL diagrams of the outer solar system orbits. Again, I don't expect that we'll see this, partly because pretty much every physically possible orbit in the solar system is already populated. But we hopefully will find more interesting objects in very unusual orbits. For example, there are some retrograde near-Earth asteroids known. I don't think there's anything retrograde in the main belt, so we might discover something like that. But probably not a whole lot in this category. Now, new types of behavior is much more promising. It's essentially not a question of whether we will discover new types of behavior, but exactly what types. One category would be objects suddenly appearing or disappearing. The most likely cause of that would be dust emission. So an object can suddenly brighten because it develops a cloud of dust around it because of an impact, because it suddenly started exhibiting cometary activity when it hadn't before, or because of Yorp fission. The Yorp effect is a radiative effect that can cause the spin rate of a small solar system body to increase until it experiences some kind of centrifugal failure. That's one thing that can cause it to emit a bunch of dust. And the sudden clearing of the dust is one thing that could cause an object to disappear. But objects can also cease to exist. A solar system object can disintegrate completely. So that's something we might also see. So new associations of objects. This is a category that I am particularly interested in part because it's nearly guaranteed that we will find these things. So the most likely type of new association would be a new asteroid collisional family. Collisional families are groups of asteroids that share similar orbits because they are all pieces of an asteroid that were shattered in the past. And there are simulations of the main asteroid belt that indicate the fraction of asteroids that can be traced to a collisional family increases toward 100% as you go to the very small sizes. And of course, LSST will probe those very small sizes. So it's likely that we will find some young collisional families that we haven't seen before. And this will tell us interesting information about the recent history of impacts in the asteroid belt. There are also asteroid pairs one of those is illustrated here. And it's believed that this is an extreme form of Yorp fission, where an asteroid speeds up, the rotation of an asteroid speeds up because of the Yorp effect until it splits into two. And what's shown here is the separation in position and velocity for one of these asteroid pairs integrated back through orbital history. And this corresponds to about 7,000 years ago, this downward spike. And it gets so low, so close, that effectively at the level, the precision of our data, this is probably 0. So it probably was one body 7,000 years ago. It's split. There's likelihood that we will see a lot more objects like this in LSST. Interstellar objects I'm not going to cover. So a few comments, some of them deliberately a bit provocative on how to find the unexpected. So I would say that computers, machine learning, it's very useful potentially, but only humans can discover. And what we should use our computers for is to sort through the bunch of normal, uninteresting stuff and provide us with these culled down lists of things that are worth looking at more carefully. Also, I think it's desirable to involve people at different career stages in this kind of investigation because absolutely experts see more than beginners. They see things that beginners don't see, but they can also be blind because they know what to expect too well. And someone who's bringing fresh eyes to the data, someone who is not an expert, can see things that the expert cannot see. Also, I think it's important to write fast, efficient code. And I mean, even more efficient than you think it needs to be, gratuitously efficient code, because that will allow you to search regions of parameter space bigger than you might think you need to. Search it, including regions where you don't expect to find anything, where you know there's nothing, because sometimes what we know might be wrong. And there are examples of this from astronomical history where by looking somewhere there shouldn't have been anything, according to our best understanding, we found something really cool. That concludes my talk. Thanks.
Thank you so much. All right. And I want to say that I asked you to do this quite at the last minute. So I very much appreciate that you stepped in to cover solar system. Questions from the audience in the room? Questions on that? Great, because I had a question and I was dying to ask. So you've talked only about, you talked mostly, if nothing else, about orbital anomalies. Is there something that, we can learn from, even if the orbit is regular, like in the time domain for these objects or in the morphology for these objects, except for ISOs that obviously have morphological?
So one thing that I skipped over in the interest of time would be objects that appear or disappear because of rotational light curve variation. So Oumuamua was extremely elongated or flat or something, and it varied in brightness by a factor of more than 10. There are solar system objects, very few, but solar system objects that have been seen to vary in brightness by up to a factor of 20. So typical asteroid rotation periods are hours to days, but there could be ones that there are asteroids that have periods of weeks or months, rotation periods. So something like that, if it has a very elongated or flattened shape, it could disappear or suddenly appear simply because it was rotating, and it rotated so that it's exposing a larger angular cross section. Suddenly we can see it, or suddenly we can't see it. So there are morphological reasons why we might see these very surprising anomalies.
Thank you. Let's thank Harry again. And next on deck is Angelica. Are you here? Angelica? Okay, well, oh yeah, I see you. It's you, Angelica? I'm mispronouncing your name terribly, so Agnieszka. Yeah, that's you. Sorry, because I've seen your name spelled a couple of ways and I'm very confused clearly. So Agnieszka Polo to talk about extragalactic anomalies.
Thank you. And so my name is Agnieszka Polo. Sorry. And yeah, here I thought that it would be a bit apropos to tell about the work, which is actually not so new, but because it was this is a paper from 6 years ago, but still a bit in line of what's happening. And it was actually done with the LSST in mind, so maybe it's can serve as the inspiration for the next steps. And the main author here was Solash, who sadly left astronomy since then, but she did really an excellent work here and not only here. And here the idea was to treat the data from the Wide Field Infrared Survey Explorer, WISE, the infrared satellite data, as a kind of proxy to the LSST, not in terms of the data, but in terms of numbers, because this is a very numerous catalog, and to see how we can find something unexpected among the numerous detections, 747 million sources, which are in the all-WISE data. Truth is that after selection and cleaning of the data, we were left with something like 250 50,000 million sources, but still it was a number big enough. And here, yes, instead of looking at something which would be like usual color catalogs, we thought that looking for something unusual, given the amount of data, may be promising. And here the approach was with, well, first of all, okay, I probably messed up with the order of the slides, but never mind. So the approach was to try a semi-supervised method, which was the one class SVM method, and this requires a training set because its assumption was that you just divide the data into two classes, something which is similar to classes you know and something which does not fit. So for the training we used the SDSS sources, everything which we could cross-correlate reasonably with the WISE data, galaxies, stars and quasars. And then we have chosen the parameter space, nothing refined in this case. In this case, we used some experience from yet previous papers, and what was looking promising based on those previous papers was the combination of brightness in the most nearby to the optical band, color and compactness. We didn't use all 4 WISE bands, but only the 2 of the best quality. And then we tried to look for these unknowns with this method I mentioned. Relatively simple. This is a linear method, just trying to find the hyperplane, because what would be all known and what could have been classified as unknown. And as a result, out of this 2.5 million data, we found quite a large number of sources which could have been classified, could look like anomalous sources. And here you can see that even by eye, they are divided into 2 classes, one bigger, one smaller. And then the next question was, what are they? And then looking at the larger of these clouds more closely, we find that basically this is a trash bin. So these are sources which are mostly spurious, blends and such. But here the point is that these spurious sources escaped all other searches for spurious sources. So they were not classified as such before. And in this way, we may say we could clean the catalog. But then this other smaller group, in some part also was composed of spurious sources, blends mostly in the galactic plane, but a majority of among these 30,000 sources looked quite normal, looked quite nicely in the data. So then the question was what they were. And our working hypothesis at first was that they may be dusty AGNs. And then there were some follow-up observations. And the follow-up observations were only for a small part of them. But the conclusion was that they are actually quite varied sources. So maybe more interesting, but not as simple to predict. So some of them were indeed, like we expected, dusty AGNs. Some were very low redshift and very dusty galaxies, and some were just galactic objects like very dusty young stellar objects. So a combination of things which was somehow not predicted by the DSS, maybe rightly, because all these objects are dusty, so SDSS simply does not see them, does not classify them properly. But in that case, it seemed to work. So then my plans back then were to push it further for the LSST, but you have only as much as manpower at once as you can have. But still, I think that there are some things here which can be applied, and then I would be happy to join. Thank you.
Question for Agnieszka. Yes, Konstantin.
Thank you so much. Have you checked sky distribution of anomalies you found?
Yes. So I was showing it somewhere here. So here, oh, sorry. So here I didn't mention one. These most problematic sources are mostly in the galactic plane. For this more. For this smaller group, some are in the galactic plane, and these are usually problematic, but the rest, as you can see, is distributed on the sky quite uniform. We even went further because I don't have the slide here, but we computed correlation functions for these distributed sources, dividing them into red and bluer, and it was actually quite consistent with the assumption that they are more dusty and less dusty than the IGNs.
And Will, do you have a question as well? We're
yeah.
doing fine with time. Go
Okay,
ahead.
thanks. Yeah, thanks for the talk. Would your methods also work on DECAM data? That might be an interesting precursor for LSST type.
Yes,
Right?
yes, I don't see why not. It's just a matter of the choice of the parameter space.
It might be interesting to find the data set.
Yes,
slightly from there.
yes, exactly.
Let's thank you. Let's thank Agnieszka again. And Konstantin, you're next. Pasta Malanchev, new link project scientist.
Yeah, hello everyone.
And we're going back to time domain.
Hello everyone. My name is Kostas Malanchev. I'm just started at CMU as Link Frameworks project scientist, but I will talk about not about these exciting things I've done in the last 10 days as a project scientist in Link Frameworks, but about what I did as a part and what we are doing in SNET and what I did part of SNET team. So first of all, everybody here would like to define anomalies. I would like to define them as well, because why not? Yes. And we will find the most anomalous definition of anomalies. So first of all, of course, we could say that anomalies is something which probably is sampled from mechanism we don't know and don't know well. Yes, so something interesting we haven't studied well. Yes, and from this point of view, we could say that anomaly detection is actually kind of the same thing as discovery. Yes, so we're finding new things, and we still do not know much about this. And I agree with Ashish in his definition that it's probably only top of the iceberg. Yes, and also from some point of view, anomalies and what we tell anomalies cannot be, defined in mathematical or physical way. It is a social construct. Yes, we say that it is anomalous if we don't really know what it is, right? And today we don't know, and tomorrow we already know. Yeah, so something like that, and it is not anomaly anymore. And anomaly is what expert decided to be anomalies. Ari also already mentioned. Pretty agree with it. So my definitions are not very anomalous, as you see, consistent with other people, more or less. Okay, so what we do, oh my God, all rows go quiet, super nice. Okay, but at least everybody could see arrows. Sorry for this. So
it's my fault because I forced everybody to use Google Docs for convenience.
Yeah, I'm sorry. Okay, so anyway, so we started SNET. Oh, I haven't set timer, so please tell me somebody if I'm talking too long. So we started SNET project as a project for finding anomalous object by using their light curves, and started with supernova. That's why it's SNET, supernova anomaly detection. But then we switched to some general anomaly detection in ZTF data releases, and pipeline is quite straightforward. We have light curves, we process them, then we have some outlier detection algorithm. It gives us candidates, and our experts consider them, but not just looking the same light curves as machines saw, but looking into additional data using SNET Viewer. You could find poster about SNET Viewer outside. So which provides you images, metadata, cross-matching with catalogs, so doesn't provide simulations, but you could do simulations. You could do a follow-up observations. You could go to literature, you decide something, and we also apply active anomaly detection. So this answer go back to the machine, adjust the machine. For example, if produce something we are not interested in, I'll talk about it later. And then we find something interesting stuff and write paper. Quite straightforward, but with a small loop inside. Okay, so what? Okay, about active anomaly detection, as I said. So the idea is like this. So what if our outlier for our algorithm is not really interesting? What is it? If it is some kind of artifact, bogus, or just regular object which our machine learning algorithm believes to be outlier, to be anomaly. Yeah, we could we could say our machine, we can train our machine to discriminate such objects and to try find more interesting objects and to not waste experts' time analyzing again and again the same type of bogus light curves. So it is how we build active anomaly detection algorithm without technical details today. Ask me if you're interested in technical details. Okay, just for justification, very quick summary of what we have found in ZTF data releases. So we found some transients and at least some candidates because we use archive data, so we cannot do spectroscopical follow-up, but we submitted something like 150 probable supernova and agents to TNS, and we found also 2 superluminous supernova candidates, and it was fun. We published one, and then paper with spectra appeared. So we found superluminous supernova and got spectroscopical confirmation something like 3 years after object appears, just because people, hold the data and didn't publish paper. So quite fun. Okay, and a lot of other stuff, including variable stars, M-dwarf flares, because ZTF data releases have great high cadence survey data. So working on things like this. So we just had our SNET 6 workshop during 1 week. It was just 2 months ago, and we found and published research note with a couple of interesting objects we found during this week using our new algorithm. So for example, very nice micro lens candidate, I would say binary, but I'm not expert. And below you see in the snap viewer, you could load Pan-STARRS, Gaia, and ZTF data all on the one plot, and you see very interesting counterpart of radio source, which has this linear decay. Probably it's Boyajian, I don't know. So I'm not expert, so but looks fun, at least. Very fresh results, so we haven't really analyzed them properly. Okay, so of course you could find a lot of artifacts and bogus events. So, if I type this one, will we see animation? Oh yeah. So for example, all kind of stuff. So you could see asteroids, then light curve will look like this. Yes, of the star accumulated by asteroid. You could see bogus events caused by double star defocusing. You could see some funny stuff when you have a mirror. So here we have bright mirror star and some not so bright and probably not variable stars around, and they just contaminated by this star variable, by this bright variable star, and you see correlated light curves appearing, which looked very weird and anomalous. And of course, a lot of light curves damaged by, bad detections, yes, by a lot of image artifacts. We have a nice art collection on this webpage. Would like to see some cool stellar art. So my last slide. So I hope I'm more or less in time. So if you deal with real data, why it is important to check our algorithm on real data, you'll find a lot of artifacts, bogus things, and so on. And that's why we should always try to check our algorithm on real data. And maybe we could use these artifacts and bogus events, yes, to make our photometric pipelines better and make our pipelines better. So active anomaly detection, when you have expert in loop, is so much better. So this plot shows it's somehow, so green is better than orange. You see it, and green is active, orange is not active. So one interesting result I haven't mentioned that we reported 16 probable supernova which produce no ZTF alerts. So the alert brokers have never seen them. For example, this thing, which really looks like supernova and produced 0 alerts. You find 0 data in alert brokers about these objects and 15 other. And the most important thing to learn that anomaly detection systems must be built for experts. So they should, when you build anomaly detection system, you must think how experts will use the results it provides. Okay, thank you so much.
Thank you.
For attention.
Thank you, Constant. Questions for Constant? Ashish.
Yeah, I have one comment and one question. The comment about the missing supernova, one possibility, for instance, is that it could be because of the templates. So if the template has a bright object, then
right, but you see, it started after. Okay, it could be so. Yeah,
right,
I agree.
That's one possibility.
But
question,
it's
yeah,
important knowledge for LSST,
Yeah,
at least for first year of LSST, if it is caused by templates.
So I had one question about the active part of your anomaly detection. You said that experts are looking at things, and when they flag something as not interesting, then they can make fewer of those kinds come through. So how do you determine the distance between what has been marked as bad and what is coming through? How do they determine the similarity?
Okay, so this is a great question. We don't have distance because it's based on isolation forest. Yes, so we don't have distance measure in our feature space. Yes, but so we usually do it saying, okay, we discriminate these trees which give us this object as anomaly. Yes, so and this way we're trying to discriminate this group of objects surrounding this given light curve. Yeah, so things like this. So we don't have formal definition of, yeah. So thank you, Ashish.
Any other questions? Any other questions? So then let's thank Kanta and then The next speaker is online, Ashley Villar from Harvard. Can I do a sound check? Can you speak up? And let's see if
Yeah,
we
can you hear me?
Can people in the back hear Ashley?
Can you hear me?
All right. It sounds good.
Okie doke. I'm gonna leave it like this instead of full screen if that's okay. So yeah, thanks so much. Sorry I can't be there this week. So I will talk pretty briefly so that we have lots of time for chatting as a community about anomaly detections, also for time series, but focusing mainly on extragalactic, in particular, this is important, transient sources. And I too will begin by defining an anomaly. I also want to say I completely agree with so many of Kostya's points that it really is a social phenomena and experts must describe this. I also agree that having expert input like greatly increases your purity of anomalies, whatever that even means. Nonetheless, I will attempt to do this in a mathematical sense. And so I want to say that in general, a lot of techniques, at least I think about, are specifically on these so-called out of distribution anomalies, which this cartoon I made represents. I maybe have different types of supernovae that I'm showing in gray and red, and maybe I plot them in some sort of space where I extract some features from the light curve and try to collectively show all of them. In this cartoon, I've asked the question, how long do the supernovae last for? And what's the overall luminosity of those supernovae? And then if I plot them all, I get some kind of clustering here. And then maybe I see some new guy. And I can think of lots of methods that help me find this new guy who's really far away from everyone else. The issue is that you can also have what we would, as an expert, call an anomaly that doesn't stick out as out of distribution. So imagine that its duration luminosity were like pretty normal. When I took a spectrum, I had lots of emission lines or something. Some really strange additional physics is happening. So in this case, I would argue that you could fix this problem by maybe just being a little bit more clever in the axes. So make sure we notice I've just changed the name of the axes here. Pretend instead I could measure something like the mass of the progenitor star that exploded, or I could measure the energy of that supernova. Then it might be the case that this thing, which was originally hidden, becomes an out of distribution anomaly. And that's kind of the philosophy that the approaches I thought about take. So in particular, one of the issues is that when we look at all the transients LSST discovers or will discover, there is no physical model to rule them all. Like even the concept of progenitor mass and energy doesn't really make sense when you start comparing variable stars to supernovae. And so we want to do this weird transformation of observables to some interesting, I'm going to start calling it latent or unseen parameters. But we don't know what the physics behind that transformation looks like. And for that reason, I tend to turn to data-driven models, in particular neural networks. And the way that this works is that, and I'm really skipping all of this, but we train a special type of neural net called an autoencoder whose job is really just to like reduce the dimensionality. Just like an expert would look at the light curve and measure a duration, my neural net is going to look at the light curve and measure some representative feature of that supernova that captures relevant information. The difference is that there's no physical input here. It's just going to look at lots of examples of supernovae to figure out what those latent features should be. If I do that, I'm making the same plot I showed before, but now my axes are meaningless feature 1 versus meaningless feature 2. I think I've deleted my citations here, but I want to just very quickly summarize a project where we did this. We used the wonderful plastic data set that several people in the audience helped build, and we just took all the supernovae and AGN, and we asked the question, if I do this neural net approach, can I find anomalies that are physically interesting? Even though I've chosen features that, like as an expert, I don't quite know what they mean. And how we do it is we train this autoencoder to make this type of plot. We plot all of the supernovae. We've very cleverly made our neural nets that most of the supernovae live in this cloud, but then some of them live way out here. And we use a random forest algorithm to basically isolate these guys living way out here. And then we ask the question, are these physically interesting? And the short story is, yeah, on average, so our purity is about 50% of the time, they are like very rare classes of physics. And what's fun about this is we were very clever about the neural net architecture so that we could update this like space as we received more data points. So a supernova with 1 data point can be plotted in the space, and a supernova with 100 data points can still be plotted in this space. So I can almost watch supernovae as they evolve in this space. And we found that we can identify anomalies in real time. So that was fun. Super quick. I want to highlight that we've really like built off of this pipeline structure to think about other problems. So one that one of my students, Lian Chen, led was to perform a similar study, but for real data now, ZTF data, specifically a variable star catalog, to try to find these anomalies with these neural nets. And this is published, but we've just been sitting on this data of like really bizarre stars that seem to be identified. They look like they're evolved, they're highly dusty, they're highly variable. We haven't really done much with them though. So like, please reach out if you would like to do something with them. But this seems successful. This really does seem to pull out a strange and not trivial set of stars. Here I'm showing like a subplot, so it looks like we've done something really easy on the color magnitude diagram, but that's not true. We're not showing all of the Gaia data right now. Okay, I do want to say just one fun thing about what I'm thinking about for the future, which is like I made this point that the space we make with the neural net is kind of physically meaningless. And I argued, well, that's because we don't have one physical model to rule them all, but that's like half true. We actually do have some physics that we think should be true across the universe. So for example, I know what cosmological redshift does to any object. I know that time gets dilated. I know that the photons look redder. And so we've been thinking a lot about how to fold that physical knowledge into these latent features so that they're still not, we don't have to exactly know the physical model, but they can at least maintain some symmetries or some known truths in the universe. And so right now, I've just skipped this slide just to say, there's lots of ways we could think about doing this. In particular, the way this neural net's trained is it's not super smart. It just tries to minimize some function. In the example I showed you, its whole job in life was to minimize the difference between the model from that neural net and the data. But you could imagine just adding what are called regularizations or like more parameters to what it's trying to minimize. For example, I know supernovae should cluster, they should look similar compared to variable stars. We could think about making that encoded in the space and force those supernovae to cluster, force those variable stars to cluster. We can also, as I hinted to before, make sure we conserve these symmetries or invariances that we have, such as, let's be invariant to redshift. If I'm a type 1a supernova at redshift 0.5, I should be in the same place of that plot as redshift 0.1. So that's what we've been thinking a lot about. And our hope is that that helps us identify more interesting anomalies to the experts in the room. So I will end there and happy to take questions if there's time.
Thank you. Thank you so much, Ashley. There is time for one question. Well, I have one.
Okay.
So you said you use a random forest in the meaningless feature 1, meaningless feature n.
Yeah.
Even if the features are meaningless, is a distance method appropriate? Would the distance between the features be meaningful? Does that make sense?
Yeah, that makes sense. Is the distance meaningful? Is the distance meaningful? I'm going to say probably not in this case. And I think if this were trained a bit better, in theory, yeah, you could have distances that are meaningful. In this specific paper, because you can see with your eye that there's no clustering that happens, even though I know there's about 10 physical classes in here, this suggests to me that the algorithm was dominated by this prior that wants it to be one cloud of points. And so that suggests to me that here the distances probably aren't super meaningful other than the distance from the center. So the farther away I am, probably the weirder I look, but I can't really disentangle like physical classes.
Thank you very much.
Yeah.
Let's thank Ashley one more time. And we have this is it for the long ish talks. Thank you very much to all the speakers. We do have a series of 1-2 sliders, including one recording. But to make the session a little bit more active, even though we won't have a lot of time for discussion, I want you to think also in parallel as you listen to the next 4 speakers of one thing. I want you to think of what is that one kind of anomaly that you think we have the highest risk of not detecting in Rubin. What kind of space does it live in? Is it time domain? Is it proper motion? Is it any of the other spaces? And I would like you, if you can think of something, to put it on our Slack channel. And then maybe that can spring some discussion that can happen asynchronously after the talk. Was that clear? Awesome. So let me see if I can successfully show you a video. Chris Linton has kindly agreed to talk to us about another case of anomalies in the solar system. However, he is at another session presently. So he gave us a recording. And I am not entirely sure if online you'll be able to hear the recording as we play here, but it's in the slide. So rather than trying to fuss with the presentation setting and share the sound, which will cause an echo in the room, I would like the people online, if they could just like, you know, play the recording for themselves. It's about 3 or 4 minutes long. And let's see if I can play it in the room and if we can hear it on site.
Hello, everyone. I'm Chris Lintott from Oxford. I want to quickly highlight some work done by Brian Rogers, who's a Breakthrough Listen funded summer student from Queen's University Belfast, who's been working with me this summer on finding the unusual stuff in the Rubin view of the solar system. This is a complicated project because of the diversity of objects that Rubin will find, and in fact, the sheer number of them. We've used as input for this work the measured colors of a simulated Rubin solar system, but also the orbital parameters. So we're assuming that these are things that the Minor Planet Center has assigned hopefully reliable orbits to. That creates a very multi-dimensional space with which to represent our data, and we can use standard modern machine learning methods to drop that down to a 2-dimensional space so we can view it. That's what you're seeing on the right here. So every point here is an object in the Rubin solar system in this 2-dimensional space with fairly arbitrary axes. And the first thing I want to point out really is that in this sort of problem, there are many definitions of what an anomaly could be. So if red here represents normal faces of normal objects, we've added in objects at the ends of the distribution, but they come in different flavors. So in yellow, you've got global anomalies. So these are things that stand out in one or more of the parameters, presumably some combination of them. So this is sort of our traditional anomaly view. But in the solar system, we also care about local anomalies. So we might care about particularly unusual near-Earth asteroids or the strangest members of the Kuiper Belt or things like that. So they have to be identified in context. We also care, I think, about clustered anomalies, so about new families of asteroids, for example, which may be populated in the Rubin solar system, but as yet unidentified. So this is a complicated problem, but it turns out to be tractable. So we've used a variety of different machine learning methods to attack this. So one of the things that Brian's done is create a Gaussian mixture model representing this multidimensional space. And then we can look at how isolated something is compared to other members of that model. And so that's the y-axis. So that gives you an anomaly score. On the x-axis here, we've used an autoencoder, and we can see how difficult it is for that model to reconstruct a particular member of the data set. So in other words, how difficult it is for the autoencoder to learn to include these rare things. So that's the y-axis. So this is a meaningful two-dimensional space. And what you can see here is that a small number of objects are isolated in this 2D space. So those are our anomalies. We're actually only plotting the top 1,000 objects here. But you can see even within these top 1,000 most anomalous things, there are some objects, and we've had a look at them and they make sense. So in the top right, you've got the most extreme examples in a particular color combination used by people who study the solar system. Bottom right, you've got a different set of outliers in color space. But along the left-hand axis, we find unusual things. For example, we find a set of near-Earth asteroids with unusual orbits, things worth looking at. And a bit higher up there, I'm very excited by, I think it's number 6 here. This is a Trojan asteroid that stands out because it's got weird colors. So we're genuinely finding things worth astronomer attention, worth follow-up, using a hands-off approach. There's nothing in either of these models where we've told the models what sort of anomalies we're looking for. The next step will be to apply this to DP 0.3. Thank you for the hard work getting that out, everyone. And in particular, I'm excited because I know that Mario and co have hidden at least one technosignature, alien spaceship, within the data set. So hopefully, when we make this plot for DP 0.3, it will pop out. Sorry, I'm not here. I am next door presenting at the EPO session, but I am around the rest of today and tomorrow morning and on Slack if any of you would like to chat about this. Thanks for your time.
Let's thank Chris, even if he's not here, just symbolically. And he is at the conference, so you can find him as he mentioned, and also please continue asking questions on the Slack channel. Ashish, your quick slides are next. And then
I'm Chris Lintott from Oxford.
Sorry about that.
I want to quickly highlight some work done by Brian Rogers, who's a Breakthrough Listen funded summer student from Queen's University Belfast.
Stop. Okay. Let me see if I can go to the next slide instead of this one. And one before this, yes. And Abby, you are on deck next. And sorry, give me a second to screen share with the Zoom participant.
Hello again. My name is Ashish Mahbal from Caltech, wearing my hat now as the ZTF ML lead. So one of the things that we have been doing is looking for anomalies in the ZTF data. ZTF, as you know, covers in a single image 47 square degrees, and we have several hundred observations each for the entire northern sky. And now what we have been doing is that looking for anomalies in individual fields. The way we do it is that we have catalogs from the light curves. We create features, and in the features, then we run a large number of binary classifiers. And then in these binary classifiers, we look for objects that have been classified confidently, at least in one class. We'll be going to more ambiguous classes later, but at least one class. And then to that, we apply HDB scan and isolation forest. And then we look for overlapping objects found as outliers with both of those methods. And on those common outliers, then we look for additional features, combine some additional data, and that is what we are looking at as anomalies right now. And to look for additional things, or the way to isolate further things. So those are the ones that were all found as outliers. And within that, then this is a UMAP, which is like Disney. We find many different arms. And because we are looking for objects that have high confidence, at least in one class, most of these objects are in-class outliers. But because we are not restricting them to a single class, they do have interesting objects that can belong to two classes. And in fact, some of these objects we are also starting to put in the game that we have developed called Zarth, which is available on Androids. So you can experience some of these anomalies live. Every day, new fresh objects from ZTF are put in. These are called wild type 1 and wild type 2. They belong at least to two different classifiers, claiming them as themselves. So these we are putting together in data sets, and we'll be looking at closely. We have not taken many spectra yet, but that's the process that's starting to happen soon. And I'll stop there. Right. Thank you.
Thank you. I will propose that we ask questions on the short slides at the end. So Abby, you're next, and then Consta, you're on deck.
Thank you. We need a slide.
Yep.
So I was talking with Fed yesterday or day before, and she twisted my arm to talk about something that's, from my perspective, a little old, but it might be of interest, and so I've agreed to talk about it. Some years ago, we did a time domain survey of the galactic, of some fields in the galactic bulge with DECAM, and in particular, the field that sits on top of Bada's window. I'll talk more about it tomorrow morning in Clarkson's session, but we found in this field something like 2,500 variables, many of which actually were known and classified before by Ogle. But anyway, we used a method that was originally formulated by Ashish to look at what's called DMDT. So basically on the x-axis of these plots, you have the delta log t, so that's the interval between any two measurements. And on the y-axis, you have delta m. Now, delta m doesn't have to be in the same band. It can be across bands, even if there are different times, because there's information. And so these multiple plots sort of look at not just in the different bands, but also differences across bands. And this is these plots, I think, are of the whole set of objects. And so you see here a distribution. Now, if you were to get an observation that happened to be over here, you would say that was anomalous, right? But in most cases, we can classify. If we have the whole light curve, we can classify things. But the chances of getting something, and you would only find something anomalous if the amplitudes, either in color or in amplitude, were very large. So the thing is, I think that you're interested in finding objects, particularly transient phenomena, as early as you can. So you want to get them out of 1, 2, or 3 observations. So we thought of other ways of doing this. This is just the first order, this is 0th order DMDT. And we thought, what about D2M dt squared? So what does that mean? That means that, let's say I have 2 observations, 3 observations. So I have a triad, I have a delta T1 and a delta T2. Those are given. For corresponding to delta T1, I have a delta M1 and I have a delta M1 and a delta M2. Now here I've got just an example of something that is periodic with a half-a-day period, say. One is sinusoidal and one is a sawtooth. And if I then take these things and say, what is delta M1, delta M2 going to be as I move across in phase, I get a distribution of points for the sinusoidal one and for the sawtooth one, and you can see how different they are. And so we think that this might be at the basis of being able to characterize things by the shape of the light curve without actually having the light curve itself. And you're basically asking, are these 3 points consistent with a light curve like this, or a light curve like that, or something completely different? I'll leave that as a nascent idea and stop there.
Thank you so much, Avi. There's a thread on Slack that, Avi, I encourage you to monitor with your name on it for questions on your slides, on the Slack of the meeting. Consta, you are presenting on behalf of Patrick Aleo, student.
Sorry for this. So I'm presenting on behalf of Patrick Aleo, who is grad student at University of Illinois. I haven't participated in this project, but I was in this group before, so I'm trying to explain it really fast. So what is happening? It's anomaly detection filter, so a code running versus every new alert coming to Antares alert broker from ZTF, and using light curve features and host galaxy features, like shape features and magnitudes and everything like that for the micro redshifts if they exist. And so it is trained to work better. So it's not trained to work better. It's developed to work better with extragalactic transients and built to have high purity of anomalous anomalous transients of known types, such supernovae, and they will be and there is ongoing, work on making working better. And the example you see is probably object from 2020, so it was in kind of training set, but to say validation set of this algorithm, and you see that it triggered this filter triggered this object just before the second peak, which is quite nice. Thank you.
Thank you, Constant. And thank you to all the speakers. We have 3 minutes left, which isn't enough time for questions for all of our 4 speakers. So I'll defer those to conversations in the hallway and Slack, but I want to continue my sociological experiment. I'm going to ask you, I will count to 3, and I'm going to ask you to just say out loud what is the kind of anomalies that you're worried that LSST will miss. And I will say what's the kind that I think it will miss. And if you leave me alone and I'm the only person speaking and nobody else shouts out the name, I will be very sad and feel very silly. So please, at the count of 3, say a word associated to the kind of anomaly that you think LSST will sadly miss. Ready? 1, 2, 3. Aliens.
Short.
Thank you. I didn't hear any of yours, and I'm sure you didn't hear mine, but I want to encourage you all to have this conversation. I think I don't want to take any of the meeting time to say something obvious, but to me, LSST is the most exciting thing about LSST is the potential to expand the discovery space and discover unknown things and lead us to new physics and new phenomena. So if you want to talk about these things, the TVS subgroup, the ISSC working group.
So I in fact say that ISSC working group come to it to contribute something and or to bring problems to us, because that would be also interesting.
Exactly. We can talk about methodology. We can talk about potential anomalies and, things that are barely known and that we want to make sure we understand better. We can talk about how we go from the detection of anomalies to understand the mechanism that produce them and make them anomalies, which is going to be the hardest part. And with that, I think we are done with this session. Thanks, everybody.